Okay, let's get started. This Monday we discussed the DSB-SC, right? Double sideband suppressed carrier. So we are still talking about amplitude modulation, right? And this is one of the amplitude modulation, and possibly it's better than the previous amplitude modulation. And still, since we are talking about amplitude modulation, your message MT is still part of your amplitude side of the carrier. Okay, here we see carrier, and we multiply the amplitude into the multiply the message into the amplitude of the carrier. Right? Still, the message is part of your amplitude. But compared to the previous amplitude modulation we discussed, the difference is that in this case we simply multiply these two. Okay, and in time domain we just simply multiply like this, and you make a ST, and this ST is what you transmit over the air. When you look at this one in frequency domain, and we see that we have two different terms, right? Positive and negative frequency. Okay, so as simple as that. If you visualize those things, this is MT, the time domain message, and you multiply the carrier, okay, the cosine carrier into here, then you'll see this kind of ST, and this is what we transmit over the air. And remember that we have a phase reversal here because the message sometimes goes to negative, so you may see the phase reversal. When you look at this one in frequency domain, this is our original message in frequency domain. Now, by multiplying the cosine, you convert this message to this. And now, when you look at that same thing, the frequency domain, we are doing modulation or the frequency shift. So now the original message in baseband is now shifted, and now the center carrier becomes FC and also minus FC. Right? And remember, this one, let's say, is 1. Then because the energy is moving left and right, half and half, now the top here, peak, is going to be a half, right? 1/2, you see that. So this is SF, and this is ST, okay? So this is time domain, this is frequency domain of the signal you transmit over the air. So this is what you transmit over the air, the same thing, but in the frequency domain, okay? Now after you transmit such a signal, we need to think about how to receive it. Okay? This is a receiver. The previous one was a transmitter, but this is a receiver. You receive the ST, okay, the signal that we just looked at, ST, and this ST comes in to the receiver, and in the receiver, first thing to do is multiply the carrier again. Okay? The same carrier. The same, what that means is we are using the same frequency, which we call the carrier frequency, right? So we are multiplying same sinusoidal frequency or carrier. Amplitude doesn't matter, really, it doesn't matter because it's going to be, it's just constant anyway. So forget this amplitude, it's not important. Important thing is you are using the same carrier frequency because we basically agree, right? Transmitter and receiver agreed what carrier frequency you use. So both one knows, transmitter, receiver both knows that what is the carrier frequency. So you generate your own carrier frequency using the oscillator and you multiply. Okay? And possibly the phase may be different. Why? Because at the transmitter, you are generating your own carrier frequency and transmit, right? And at the receiver, again, you are generating, FC is known for both sides, but you are, at the receiver, you are generating the carrier frequency of your own. Okay? So two different sides generating a carrier frequency of your own. Okay? Each one differently. So the phase may be different. Now you multiply that, then you see the VT right here, you see it's kind of cosine square, right? Because ST was already have a cosine. Now you are multiplying cosine again, then you will see cosine square. Okay? And then based on low pass filter, now you're removing the high frequency component, you're recovering your original message back. So remember the picture that we discussed, right? The whole picture of a transmit receiver. You need to remember those things. Okay, let me redraw it. So we have a message empty. Okay, in the transmitter, what you do is you are multiplying cosine. This is carrier frequency. And then you make a ST. Right? This is a transmitter, TX. And this ST is equals to MT times cosine 2 pi FCT. Now this ST goes into receiver. In the receiver, the first thing to do is multiply again the cosine, but it may have a different phase. And right here, let's call it as a VT. After that, you go through the low-pass filter. So here is a receiver, RX. What you need to remember is here, VT, and also right here. Let me call this one as M hat T. When you look at this VT right here, VT equals to ST times this one, right? So ST times cosine. But ST actually was MT times cosine. So now somehow it's like, let me write it again. It's a MT times cosine, which was ST. This one was ST. You're multiplying cosine again. But this one may have a phase difference. That's what happened here in the VT. Okay? Just simple mathematics. Now you see that this is cosine multiplied cosine, but inside here you have a little bit different because of this phase. So now what we need to use is this trigonometric identity. You have two different cosine multiplied equals to the half of cosine, addition of two different cosine. Okay? So using those identity, now you can change it to now you can change it to this way, right? Look at this first term. This first cosine is going to be the addition of the cosine parameters. And this one is a subtraction, right? So using that identity, you are basically changing the multiplication of two cosine times cosine, into another cosine plus cosine. So it's a multiplication, it's changed to addition of these two. When you look at this, now what you can see is we have two different terms. Each one is a cosine, but the first cosine, you see that the frequency of this cosine is 2fc. Okay? Originally, fc was our carrier frequency, but eventually what we get is 2 times of fc. It's even higher frequency and 0 frequency, or DC. Okay? So we have these two different terms. Now what we need to do is that we are still talking about here VT. Now what we need to do is we need to go through the low pass filter. And the reason that we want to go through the low pass filter is to remove this term, the high frequency term. We just want to kill it. Okay? Once you remove these things by low pass filter, so after low pass filter, now eventually right here. After low pass filter, we get m hat square t, right? M hat t equals to this. So that's what we get. And the reason that I say m hat t is because ideally speaking, we need to get mt right here. But this is not exactly same as mt. But it's just pretty much similar, right? That's why I'm saying m hat t, meaning it's an estimation of mt. Estimation. Okay? So when you look at the m hat t, it has a component of mt, but in addition to that, it has a half. So somehow the amplitude is halved, right? And also, you see that the cosine phi. But this cosine phi is constant. It's nothing to do with any frequency, right? So no cosine. We recover the mt correctly. But the problem now is this one is a constant, but sometimes cosine becomes 0. Think about if phi equals to 90 degrees, then this becomes 0. Okay? So therefore, depending on the phi value, now sometimes we get 0, or sometimes if the cosine phi equal to 0, then 1, then we get half of mt. So that's what we see right here. So look at the next page. We are still talking about coherent detector, right? Coherent detector. What was the definition of coherence? Remember, your phase is matched, right? Between what and what? The phase between the transmitter and the phase of receiver, right? This phase. This is the phase that you use in the transmitter. And this is the phase at the receiver. Okay? So we want to match it. We want to match the phase at the transmitter and also phase at the receiver. You want to make it exactly same. That's what we call as coherent. Okay? Phase is match. Phase is same. Okay? We want to make it that way. Why? Because if you make phase the same, like a coherent, then this phi becomes 0. Because this phi right here, I'm saying here, is the mismatch of the phase. So if both phase match, that means mismatch is 0. Then this is 0. That means we are recovering the maximum output. Okay, when this cosine has the maximum value of 1, right? When phi equal to 0. So when phi equal to 0, you're going to get the maximum output. And that's what we want, right? We want to get the maximum output only when you have a phase same, okay, at both sides. So that's what we want. That's why we say coherent detection. And remember here, we already used this identity, right? Cosine square is this one. We already used that, some kind of identity like this. So remember some kind of this identity. And right here, you see the quadrature null effect, right? What this means, quadrature null effect basically means like this one. Depending on the phi, what was the phi? Phi is a phase mismatch. Depending on phase mismatch, sometimes your output becomes 0. Or sometimes your output is maximum. Or sometimes smaller value. So that's what it is. See here, if the phi equal to phi over 2 or 90 degree, maybe plus 90 degree, minus 90 degree, in that case, your demodulated output signal becomes 0. That's the worst case, right? You get 0. Okay? And this is the frequency domain representation of your output here, right? This output. Actually, this one, Vt. Okay? This picture shows you the frequency domain response of this Vt. Okay? So just to help you, let me draw the frequency domain. This Mt, let's say when you look at this original signal in frequency domain, suppose that this is our original message in frequency domain. Okay, this is our MT time domain. This is a frequency domain. So this is our original message. When you multiply cosine, it becomes ST. So when you look at the SF, the frequency response of this, now you see that now we get this, right? That's the frequency view of ST. Okay? So this is what we received here, and you are multiplying cosine again to become VT. So this is a VT. Now when you look at this VF, so VF is the frequency of VT. Okay? Look at the VF. What does it look like? It looks like this, right? That's the picture you see here. That's the VF. Okay? Why is that? Because you are multiplying cosine again into here. Okay, when you multiply cosine, now then this guy moves into 2FC and also 0. Same for this guy. This guy also moved to here and also here, right? So that's why you see this picture in frequency domain. Every time you multiply cosine, this is what happened. Okay? Half of the energy moves to there, the other half moves to left. Like that, right? Every time you multiply cosine. So that's why we have this kind of frequency view, frequency response for VT. So that's VF. So this is a VF. Remember that this one is a half of this, right? This is a 1/4, a quarter, another quarter. This is a half. Okay. This is why we need to have a low-pass filter, right? We need to have this kind of low-pass filter such that we want to block these things, and only we want to make this guy pass, because this is what we want. This is what we want, and this guy is this one. Okay? This one. So we want only this guy. So by putting the low-pass filter, we just kill the other guys, and we only want to make this guy pass in our low-pass filter. Okay, so that's what we want. But in this case, one thing that you want to remember is that because of this phase mismatch, sometimes you get 0. In case of phi equals to 90 degree or minus 90 degree, you get 0, right? So that's the worst case, and phi equal to 0, that means that's the maximum case. But let's say phi equal to 45 degree, then you get something like this, right? Some smaller value. So depending on the phase, your output sometimes is 0, sometimes the maximum, sometimes somewhere in the middle. Okay, the size of your output is different depending on the phase mismatch. That's the quadrature null effect. Okay, why does it say quadrature null? Null, what is null? Null means 0, right? Quadrature? 1/4. 90 degrees is 1/4, right? So that's why we call this quadrature null effect. When you have a 90 degree or a quarter of the whole degree, you're going to get null, 0. Okay, so that's a quadrature null effect. Okay, that's the effect. Now we need to discuss one more thing. Why do we have this phase mismatch? Okay, let me tell you this one. Okay, this one, you need to remember all this picture, okay? I just drew this last time and today again. So what you need to remember is this picture, very simple picture, right? And also, you need to write all the mt, st, vt, and m hat t in time domain. So you need to understand this mathematics in time domain. You also need to remember frequency domain of each of them. In frequency domain, you need to remember all these things. Okay, it's pretty simple to remember. Okay, let me tell you one more thing here. I'm talking about the same thing again and again in different view. Okay, let me tell you one more thing here. Just for discussion, let me assume that phase is 0. Okay, just to help you to understand, let's say if phi equal to 0, that's the ideal case, right? That means the phase match exactly. Let me draw the picture here. Let's say my MT looks like this. Maybe my MT looks like this. Okay. What does the ST look like? ST look like something like this, right? That's ST. Okay, because you multiply cosine into this MT. Okay, so this is ST. What does VT look like in time domain? You are multiplying cosine in here again, right? So this is a cosine, and you are multiplying cosine again. So it's a cosine square. What does cosine square look like in function? Okay, in general, let's say in general, you know cosine x. We know that cosine x looks like cosine x looks like this, right? This is cosine x. We have a 2 pi here, so we have a cosine here, right? What about cosine square? In general, what does cosine square look like? So cosine square is basically cosine times cosine. Okay, cosine, you multiply cosine 2 times. So when you do that, here it's a positive, and you are multiplying same thing again. So it becomes again positive. Here is a negative value, but you are multiplying negative with negative, so it becomes positive, right? So eventually, what happens is here is a positive anyway, so it becomes positive. This negative one goes back up to positive. So what happens is it's like this, something like this, right? This is a cosine square function. Let me make it a little bit cleaner here. This is a cosine square in general. Okay, in general. Here we have 1. Here again 1. Because 1 square is anyway it's 1, right? So this is the picture in general. Okay, in general, this is a picture of cosine square. Okay. What does it look like? This one looks like a cosine again. Looks like, right? This is original cosine. But when I do the cosine square, it looks like again cosine. But what's the difference of this cosine? This one looks faster, 2 times faster. Why? In this, oh, not here. Index says what is the wavelength? What is the period? This is the period. This is the period of cosine. But in this case, here is the period of cosine. So it looks like it's 2 times faster, right? Because the period is become shorter. It become half, right? Do you see the difference? So what does that mean? That means your frequency is doubled. right? Generally, high frequency means if frequency is higher, your period becomes shorter, right? It's faster. So when you draw cosine square, it looks like right here is same as here. So your period, let's say t, now here is the half t, right? Something like that. So your period becomes shorter, meaning your frequency is doubled. In addition to that, what's the difference in this cosine? This cosine does not have 0 in here, right? It actually somehow it lifted up, right? Because in this cosine, a typical cosine, it's like from 1 to -1. It's always like a positive, negative, positive, negative. That's cosine in general. But in this case, it's always positive. So where is the middle point? Here, middle point, here's a half. Right? Half. So when you look at this, right? When you look at this, what you can find out? In this case, you know that this is a cosine, but this cosine is the double frequency of this particular cosine. Not only that, this one is somehow lifted up, so the middle point is half. So when I write this equation in general, I can say that it's 1/2 plus 1/2 cosine 2x. That's this one, right? Because why do we have 1/2? Because it's lifted up. The mean is not 0, right? Mean is 1/2. So we need to have 1/2. Plus, in this case, the amplitude here is 1/2. Because the maximum, so, okay, from the mean point of view, the maximum peak is going to be 1/2. The minimum is -1/2. Okay, so you should have 1/2. And when you look at the frequency is doubled. So it's cosine 2x. In fact, the cosine square is the same as this, right? In mathematics. That's what we looked at here. Cosine x squared is half over 1/2 plus 1/2 cosine 2x. And you can see that in mathematics here, in the graph, in general. So this is what happened, right? Right? Just in general, this is like high school mathematics. So that's what I'm talking about here. So given that, but my assumption here is phase is matched. Only when phase is matched, only when phi equal to 0, this is true. Now, let's say, now let me think about another case. Now let's think about worst case. Our phase mismatch is 90 degrees. Okay, let's think about that case. So in that case, right, cosine multiplied by cosine but with a 90-degree phase difference. Okay, so cosine times, it's like cosine x plus its 90-degree phase difference. Let's think about this one. This is the original cosine, but what I like to do is I like to draw the phase difference. So when you add the phase difference of 90 degrees, maybe you can move it to right, let's say. It doesn't matter left or right, but when you add the phase of 90 degrees, so this one needs to be shifted because we have a different phase. So when you shift by 90 degrees, it looks like a sine. Oh, 1 second. No, it's not. Something like that, right? I'm not drawing sine. It is actually sine, but what I'm trying to draw is this one. Okay? originally cosine, but I'm adding the phase difference of 90 degree. So you are shifting this cosine into 90 degree because we have a phase difference of 90 degree, right? So this is what we have. And what you want to do is you want to multiply these two. Let's multiply these two. Then see what happens. When you multiply these two, right here we have a positive, and this 90 degree phase difference one, still you have a positive. So somewhere in here we get positive value. Right here on the next, here, the original cosine x has a negative value, but this cosine x pi over 2 has a positive. So right here we get negative value, right? Here, next quadrant, you have negative, negative, so it's positive. Here, positive, negative, so negative. So eventually, when you multiply these two, eventually what you are going to get is positive, negative, positive, negative, positive, negative, something like this. That's eventually what you get after you multiply these two. So what does that mean? That means you're going to get another sinusoidal function, okay? And the period of sinusoidal function is, let's say this is t, then the period becomes half of t, meaning that frequency is again doubled. Frequency is doubled. So you will see that something like cosine 2x kind of thing. Frequency is doubled. And not only that, yeah, frequency is doubled. But the difference compared to the case when phi equal to 0, now in this case the phase difference is 90 degrees. The difference is that the mean value is 0. The mean value is 0, right? That's the difference. In the previous case, when the phi equal to 0, what was the mean? The middle value? The middle value was half at that time. At that time, this is the case, right? This was the case when phi equal to 0, when the phase mismatch was 0. When phase mismatch was 0, then remember that we have a DC component, okay, at that time. But now, when you have a phase mismatch of 90 degrees, you don't have any DC component. The mean value is already 0. So you have only this component. There's no DC. Okay? You only have this component. Now when you multiply these things, right here, we are talking about VT, right? Right here we are talking about this one. Next thing to do is low pass filter. And low pass filter will remove this. Okay? And because of that, now you're going to get 0. Because only DC component will bypass, will pass through the filter, right? This high frequency component will be removed, will be blocked by this low pass filter. So this component will be removed. Okay? So this is why. This is why when the phi equal to the phase mismatch is 90 degrees, you get 0 value, 0 output. You can see all of those things in this diagram. Okay. So this is an example in your book, right? This is the example when your original MT or MF, your original MF looks like this. Okay? So what is your MT then? It's a cosine, just pure cosine. Okay? If your message, original message is a pure cosine, as an example, just as an example, if your MT is original, MT is a pure cosine, your MF looks like this. In that case, when you multiply the cosine carrier, now you'll see that this one will move to positive and negative, right? By multiplying cosine. So you're going to get this picture. So you see that there's 2, right? In positive FC, and also another 2 in negative FC. Okay, this is the ST or SF. This is frequency domain, so you said this is SF right here. Okay, that's the picture. Now, after this, at the receiver, what you need to do is you are multiplying cosine again. Okay, when you multiply cosine again, in this case, what does VF looks like? This VF right here should look like this, right? So this is what you're gonna get. So that's this picture. This picture only shows you positive, but there's also negative here, and there are 2 more, right? So that's a picture like this. Okay, that picture only shows you these positive ones, like that. Okay? But there is negative part here. So that is VF. That is a VF, only the positive one. And this is a VT. This one is a VT. So this is actually the same thing, but this one is only time domain, and this is a frequency domain view. Same thing, we are talking about same thing. So these things is right here, VT. So this is time domain VT, and that is the frequency domain, frequency response of this one. Right? So looking at this VT in the time domain, like that, frequency domain, it's like that. Next thing to do is to go through low pass filter. So when you put this signal into the low pass filter, what is going to be output? This is going to be the output. So put this one into the low pass filter. Now the output looks like this in time domain. But look at the same thing in frequency domain. You put this one into the low pass filter. The output is this one. Why? Because low pass filter will block the high frequency component. Only the low frequency component will pass. So all the high frequency is now gone, okay, by low pass filter. So this is a frequency domain view, the time domain. Now we recovered our message back. This is our original message, okay? Because in this example, we assume that our original message was sinusoidal function. So that was the sinusoidal function, and that is our message MT in this example. Okay? So we are still talking about the same thing again and again now. Okay, this one, next one. Okay. Oh. Okay. This is next slide, right? This next slide is very important. Somehow a little bit, let's say, advanced knowledge, let's say. This is a little bit advanced, but very important one. Okay, very important. So let's discuss this one. Right here so far, okay, let me summarize a little bit. What we discussed so far is that you create the ST at the transmitter by simply multiplying MT with CT, cost carrier. At the receiver, you again multiplying your own carrier frequency and create the VT, and then put this VT into the low pass filter. Hopefully you can recover message. Now what was the problem? Phase is the problem. Okay? Sometimes phase is 90 degrees. You are so unlucky. You get 0. Okay? You did a good job, but still you get 0. If you are very lucky, phase mismatch is 0, you get the maximum output. So now what happened? This phase is random. Okay? So you did your best, but sometimes you get 0. So that's the problem now. Okay? That was the problem so far. Now this COSAS receiver is trying, it's again receiver. This part. This is a receiver, right? So this is a little bit advanced receiver. This is maybe simple receiver. But that's a little bit more advanced, a little bit more complex, right? So I'll tell you why we need this, okay? In this case, again, depending on the phase mismatch, if you are lucky, you get maximum. If you're unlucky, you get 0. So that's bad, right? Because your output is based on the luck. If you're lucky, unlucky, and this is random. So what this COSAS receiver tried to do is to find out what is the mismatch. Okay? You want to find out this phase mismatch. In this receiver, this simple receiver that I have here, there's no way you can find out. There's no way. Maybe phase mismatch is 45 degrees, but you never know. There's no way you can find out. But in this COSAS receiver, you want to find out, you want to calculate what is the phase mismatch. And once you know my phase mismatch is 45 degrees, once you know it, then you can correct it. You can make a correction. So this guy wants to do it. Once you find out the phase mismatch, then you can correct it. Once you correct it, then you always get the maximum. It doesn't matter, lucky, unlucky, you are always getting maximum value. Okay? That's what we're trying to do here. In this case, you have no way of correcting the phase because you don't know. There's no way you can find out the phase. You see the difference? So that's the difference. So let's talk about a little bit here. It's actually very simple. Okay? Very simple. The only difference between the previous receiver and this receiver is that this COSAS receiver have these things 2 times. Look at up here. We call this as I channel or in-phase channel. In this in-phase channel, you have a product modulator or multiplication and low-pass filter. And right here, you are multiplying a carrier, cosine carrier. So when you look at only up here, I channel, only up here, that looks same as this one, exactly same. Okay? This part is exactly same. But in COSAS receiver, we have one more of that. We call that a Q channel. Q means quadrature. I means in phase. Q means quadrature. Okay, we make it short as IQ. Okay, IQ, but I is in phase, Q is quadrature. So in quadrature phase, it actually is same. Hardware looks same. You again have a product modulator, and again you have a low pass filter. Okay, so we have 2 different paths, I phase and Q phase. But then what's the difference? In the I phase, it looks exactly same as this, but in Q phase, looks as almost the same, but you have one difference. In this case, you are multiplying sine, not cosine. You are multiplying sine. That's the only difference. Okay, that's the only difference. So in our original receiver, you are multiplying cosine carrier, right? Cosine carrier. Same here. You are multiplying cosine carrier. You see here, cosine carrier. But in quadrature phase, you are multiplying sine carrier. That's the only difference. Okay? I'll tell you why we are doing it. But other than that, it's pretty much same. So now let's say we are getting some signal here. Okay? Some ST in this case. We get ST. ST goes up here and also goes down here. Okay? When put the ST goes up here, then it's multiplied by carrier again and go through the low pass filter. The output right here is same as this. You're going to get this one, right? Because this one looks exactly same as this. So you're going to get exactly same output right here. So now let's assume that our phase mismatch is 0. Okay. Actually, before that, okay, let me draw it here. Okay. So this is a Costas receiver. Simply speaking, this is Costas receiver. You look at, maybe it looks a little bit different, but it's same. Okay, same thing. This is Costas receiver. What I want to tell you is that some of the mathematics behind this, because you need to understand the mathematics. That's much easier to understand. Okay. In here, okay, just to start, let's assume that if phase mismatch is 0, okay, just assume that. Okay, phase mismatch is 0. In that case, as we discussed earlier, this VT right here, let me call this is a W here. Okay, here's W, here's a V. As we discussed earlier, if the phase mismatch is 0, in VT right here is a cosine square. It's a simply cosine square, right? And cosine square is the same as half 1 plus cosine 2 pi 2fc t. Right? We are talking about the same thing again. Now by putting this signal into the low pass filter, now we get this one 0. So you're going to get only this component back. Right? That was what we discussed. Let's do the same thing for this Q channel. This is I channel. Let's say again the phase mismatch is 0. You get ST and put it here. Here we have ST, right? Let's put ST into this Q channel and see what happens. Let's look at this W. This W is ST times sine. Okay? So that means ST is originally MT times cosine. So eventually it's MT times cosine 2 pi FCT. It multiplied by sine 2 pi FCT. Okay? So this is what happened. Right here. I'm talking about WT here in the Q channel. Okay? So this Q channel, suppose that phase mismatch is 0. Right here in the WT, since you are multiplying sine at the receiver, this is ST multiplied by sine. That's what happened. Using another trigonometric identity, cosine times sine equals to MT. Cosine times sine becomes half of sine, adding these two, 2 pi 2fct, plus minus of these two. Okay? And sine 0. So sine 0 means 0, right? Sine 0. This is the output right here. This is what you see at the omega t. Right? This is a omega WT here. Now put this WT into the low pass filter. What is going to be the output? Since we are going through the low pass filter, same low pass filter, when you put this signal into low pass filter, now high frequency component is removed, right? Same thing here. This is high frequency component. This is now become 0. So what do you get? 0. Because here's a 0 anyway. Here's a removed by low pass filter. So everything is removed. So you get 0 here. You get 0. Okay? So let me repeat again. If the phase mismatch is 0, that's the perfect case, right? That's what we want. In that case, you get the maximum output right here by the I channel, and you get 0 in this Q channel. So that's what we want eventually. That's the ideal output. Maximum output here in the I channel, 0 in the Q channel. That's only when the phase is matched. Now let's think about another case. Unlucky case. Let's say now phase mismatch is 90 degrees. Now you can guess what happened, right? If the phase mismatch is 90 degrees, let's do it again. Okay? Let's do the same thing again. In that case, as we already discussed earlier, you're going to get the output 0 here, right? That's what we discussed, right? If the phase mismatch was 90 degrees, you get 0 here, right? Remember that? You get 0. Then what do you get here? You get maximum output. You can actually do it, right? Because here, let's do it. Here, you have a phase 90 degree, like that. Okay? We are talking about the phase difference of 90 degree, like that. Okay? Like that. So we, in this Q channel, we are multiplying sine. And we are now assuming the phase difference of 90 degree. So let's add a 90 degree here. In that case, we are basically multiplying sine 2 pi f ct plus 90 degree. So what is this? Now think about sine function. You shift it by 90 degree. It becomes cosine. Okay? Remember that sine and cosine has a phase difference of 90 degree, right? So when you move the sine function with the phase 90 degree, it becomes cosine. So eventually it's basically the same as you are multiplying cosine with the phase 0. It's basically the same as cosine 2 pi f ct. So this is why you are going to get maximum here, right? So you get maximum. So simply speaking, if the phase mismatch is 0, you get output, maximum output here, and you get 0 here. That's ideal case. If the phase mismatch is 90 degree, that's very unlucky case, right? In that case, you get 0 here, but you get the maximum output here. In the previous receiver, if the phase was 90 degree, phase mismatch was 90 degree, you get 0. That's it. 0, that's it, right? There's no way. If you're unlucky, that's it, 0. But in this cosine receiver, you get 0 here, but still you get the maximum here. Okay? So that's the difference. Now then, let's think about some different case. Let's say our phase mismatch is some different value. Let's say 45 degree. Just the example, right? In that case, what can you get? If the phase mismatch is, say, 45 degree, then you get something here. You get also something here. Maybe half, something like that, right? Right? So using these two output value, now what we want to find out is we want to find out phase. We want to find out the phase. How can you get the phase? How to get the phase? This Q channel, and this is I channel. Okay? This Q channel has the output of MT half of, what was that? Remember the cosine, right? This one was our output here, right? Remember that we discussed? This one was the output. And this is why when the phase mismatch is 90 degree, you get 0, right? So this one was the output. Now, what is the output here? Here the output is sine. This is the output from the Q channel. It's always like this. Think about here. Let's say phase mismatch is 0. Then let's put 0, 0. In that case, you get 0. You get the maximum output, right? Let's say our phase mismatch is 90 degree. Put the 90 degree here. You get 0 because cosine 90 degrees is 0. Here, sine 90 degrees is what? 1. So you get maximum. Okay? So you always get this output from Q channel, this output from I channel, this output from Q channel. Always. Okay? Even 45 degree doesn't matter. Put the 45 degree here, you get some output, you get some output. Now, based on these two output, how do you find out the phi? This phi. In general, we don't know, right? We don't know. What we know is that by doing this, we get something and we get something. Okay? That's the only thing we know. We don't know anything here. So how do you find out this from these two? These two we know, right? We measure, so we know that. So using these two values, we need to find out how to calculate this phase. How do you do it? Think about simple, very simple, right? You get these two values. You know these two values, right? So let's put this one and this one like put this value here, and you do the division. You simply this one divided by this. Make a division because you know these two values. Make it division like that. This one divided by this. In that case, what's going to be? It's a tangent phi. Simply tangent phi. And you already know this value. And you already know this value. So you know this value, right? Maybe this value, maybe it's like, if this value is, let's say, so you know this value, so you know this value. You simply do a division, then eventually you get this value. Let's say maybe this value is 1/3. Something like this, right? Now, how do you get the phi? Phi is arctangent of this value. Then you find out the phi. Okay, mathematically, okay? Using this one, simply do a division. Simply do division. Then you calculate the arctangent, inverse tangent. Then you can immediately find out the phi. So this is how to find out the phi. Once you find out the, that's this logic right here. We call that as a phase discriminator. That's what we do here. So mathematically like this. And when you implement that in the hardware, looks like this. This is a hardware block. But theory, the mathematics behind that is this one, right? So very simple to find out. Once you know the phi, now what do you need to do? Let's say we calculate the phi based on these things. And after all these things, let's say we find out phi is a 30 degree. Now then what do you need to do? Put this 30 degree into this logic, this block. And this block is called the voltage controlled oscillator. What that means is that, what is oscillator? Oscillator is a small hardware, small part, which make a frequency. But this one, in general, generally oscillator makes fixed frequency. It always makes one frequency. But this is not. This one has the input. That input is a voltage. If the voltage is high, this one makes fast output, fast frequency. Voltage is low, this one makes lower frequency. So this one makes a different frequency depending on the input voltage. So now when you find out the phase mismatch is 30 degree, then you put the 30 degree and you want to slow down the frequency. By slowing down the frequency, you are trying to match it. You want to correct the phase. Okay? By putting the 30 degree, you are changing the frequency, and then you want to make it match, phase match. Once doing this correction, now eventually the phase is matched, phi equal to 0, then you're going to get the maximum output all the time. Okay? So that's the hardware of this receiver. Okay? It's very important, very, very important. Okay, so let's stop here.